Thank you. Hello, everyone. Working well. So, yeah, as Daniela said, I'm from Wayve. Maybe let me start by giving a bit of an introduction about who we are. So we're based in London, and we are developing self-driving AI systems for different levels of autonomy, from L2 to L4, for those of you who are familiar with the nomenclature. And so this is the outlay of the talk today. So I'll first give a bit of context around the way we're approaching the problem called AV 2.0. Then I'll move to two research projects that we recently released, one at the intersection of language and driving called Lingo, and the other one around world modeling called GAIA, very aptly. So I don't have a slide for why self-driving is such a cool problem to work on, but I think just the human toll that traffic accidents have on society is justification on its own. And as you can see, there are a lot of actors in the ecosystem, and it's billions of dollars have been poured into solving the problem over the last 20 to 30 years. And yet, why aren't self-driving cars here yet? So we have a bunch of explanations for this. First, it's a problem that's harder than everyone imagined. It often is. It's a bit reminiscent of computer vision, which was in the 60s considered as just a summer internship. It turns out that 60 years later, we're still working on it. It also happens that actually the complexity is not only on perception, it's also the decision-making that has to be done once perception had been solved. We've gotten very good at detecting traffic lights, detecting pedestrians, other vehicles, and all that. And yet, once we have that information, the models still struggle to make the proper decision at the correct time. We're talking about, like a robot that weighs a few tons. So there's a lot of questions around vehicle integration that are not easy to solve. Regulation is also a big open question there. If I magically produced a car tomorrow that can drive itself, it wouldn't be allowed in most roads in the world, so there's a lot of work to be done there. And finally, maybe some hype has been has made us feel that the problem was closer to be solved than it actually was. But at Wayve, we also believe that there's another fundamental limitation to the approach that has been taken so far. And so we call that approach AV 1.0, and this is kind of a schematics of the approach, and as you can see, a lot of boxes there. And so we start on the left with a bunch of sensors, usually a fairly convoluted stack with camera, radar, LiDAR. Combine all of those, feed them into a perception module that has a lot of submodules. So each of these boxes has a different task and is kind of handcrafted to solve that specific task and to verify a certain set of constraints and requirements that designers have to come up with. Once the perception is done, each of these results are passed to a planning module that has a bunch of submodules. Each one of them has to be carefully handcrafted with a lot of rules. And so it's, as you can see, a fairly complex system. And once the planning is done, passed to a controller, and the controller is the one that outputs how much to accelerate, how much to brake, steering angle, things like that. And so AV 1.0, the approach I just described, has proven fairly slow and expensive to scale for a bunch of different reasons. So yeah, the perception stack has to be trained in a supervised fashion. So you need to have labels that tells you, okay, this is a pedestrian, this is a car, this is a van, this is a traffic light, et cetera, et cetera. And so it's fairly expensive to collect. And it can also be quite brittle. All these systems tend to rely on HD maps. HD maps need to be collected, so we need to send cars. People need to send cars in cities to build those HD maps, and whenever there's a change somewhere, the HD map needs to be updated, which is quite costly. The reliance on LiDAR sensors is also a fairly open and tricky question. And finally, probably the main thing at Wayve we think is problematic is that all the rules are hand designed. So you have to come up and code thousands, hundreds of thousands of lines telling you in which scenario the car should be doing this, in which scenario it should be doing that. And that's both rigid, brittle, and fairly expensive. And in parallel to all the work I just described, which could be considered as maybe more old school AI, there's been, as everyone here is aware of, a revolution in what I call modern AI. And so very impressive results across the board, right? So image recognition is kind of solved as of 2017. The ImageNet benchmark is considered to have been solved. Natural language, vision, we're seeing very impressive things coming from OpenAI, from Google, around ChatGPT, Gemini, Sora. Same thing for games. I'm pretty convinced that most games right now could be solved by an AI if like, enough resources are invested in it. And finally, for those of you who are interested in that, so biochemistry, we've seen very impressive things there with AlphaFold able to solve the long-standing challenge of protein folding. And so what are the foundations behind all these like impressive achievements? So try to put a bunch of them there. I'll go through them quickly. So first one is data sets and benchmarks. So having like, you know, like an agreed upon set of like tasks that we're trying to solve allows researchers to quickly iterate over idea and then like find what works better and then build on top of each other. Games and simulation allow to create like massive amounts of data that the models can then be trained on and all that, you know, like in a simulation. Self-supervised learning, so that one is key, I would say, to have the ability to use annotated data easily. So think of like all the videos on YouTube, for instance. You could use all of them, bearing copyright issues. I won't touch on those today. But yeah, like you have all those videos, you can train on them without needing like the costly labels that I mentioned earlier. Foundation models, so like the idea of training a generic model that has very broad capabilities that are then fine-tuned for a specific task. And yeah, scalability, so both in terms of compute and architecture, so you have bigger models, trained for longer on more data, usually produces better results. Multimodality is a big thing these last few years, so like the ability to combine video with text, etc. And finally, some form of alignment with human preferences. So something called like reinforcement learning from human feedback has been like quite instrumental to reaching something like ChatGPT. And so at Wayve, we believe that autonomous driving is at its core an embodied AI problem. So we want to leverage all the foundations I just described to solve self-driving. And by embodied AI problem, I mean an AI system that interacts and controls physical objects. And so this is the stack that we call AV 2.0, and as you can see, far fewer boxes, just one big neural network in the middle. And so we still like, you know, take in like some sensors. So for, like at the moment, it's camera and GPS, fairly simple, lightweight, fairly cheap to build. We pass that into a large neural network. The large neural network is trained using self-supervised learning and imitation on some expert data, and it outputs a plan. And that's like at its core, it's AV 2.0, so it's a data-driven end-to-end approach to self-driving. And it can already do pretty cool stuff. And so I think this, so I often watch the runs from my models in the evening, and I remember seeing this one where you literally have a car that's just gonna revert for like 50 meters in front of the model. And you know, what rule do you write for this, right? And so here, like, yeah, the model was, okay, I'm just gonna keep moving, pass the car once it has passed parts, and you know, just usual day in business. So that was quite impressive when I saw that. Another example here, one day, you know, like workers added like this big diversion in the middle of the road, and you know, an HD map would not have that information, so you would need a system that's somehow robust to it. But with an end-to-end, like data-driven approach, the model just learns, oh, when there's a diversion like that, I follow, you know, the white arrow on the blue circle, and I go around it. And yeah, this is, you know, what we believe at Wayve. We've seen like some like impressive progress these last few years, and we're excited about what's to come next. And now I'll be talking about the two research highlights mentioned before. So the first one is around language meets driving. So like LLMs, they have like a huge amount of knowledge, and in particular, they understand a lot of things about driving. And so if you ask ChatGPT, okay, you're driving along a road, a ball just comes in front of the car, what happens next? ChatGPT is gonna give a very sensible answer. It's gonna tell you, okay, you might have to swerve, you might have to brake, the ball might hit the car, causing some damage. So you have to adapt to this and always be ready for potential hazards on the road. And you can ask follow-up questions. Okay, what happens if you're actually driving next to a school? If you're driving next to a school, maybe children will come out like running after the ball, so like you have to be extra cautious, move even slower, brake like ahead of time. And finally, what if it's at midnight? Oh, yeah, if it's midnight, it's very likely that the school is closed, there won't be children around, so you still have to be careful, but the conditions have changed. And so ChatGPT has all its knowledge, like all this knowledge encoded into its weight, and you can ask questions about it, and it seems fairly natural and important to try to leverage this kind of like encoded knowledge and technologies for self-driving as well. And so we see three axes that we're currently exploring, opportunities for language in AD. The first one is explainability. Obviously, if you have a language model, you can interact with it, ask questions, and that can build confidence in like our, confidence in the system, in our belief that it's like knows what it's doing. And same thing, like combining videos, actions, and language can lead to increased data efficiency and better models that where the performance is lifted. And finally, common sense reasoning. So through words, we can imagine solving issues and what we call the long tail, which are scenarios that happen very rarely, but which are hard to learn from data. And this is where we believe that common sense reasoning from language can come into play. So explainability, what do I mean by that? You have a driving model and you have a language model that is going to interact with the driving model and be able to explain why the driving model is behaving a certain way, and just more generally explain the scene, have the ability to answer questions around counterfactuals. So what if the scene had looked like this? What would you have done then, etc. And this led us to build a first iteration on this, more of a proof of concept, I would say, which is Lingo 1. And so it's a grounded visual question answer system for driving. So how does it work? You feed in a video, which are like a few frames of images, and driving video in this case. You have a prompt, so like some text. You tokenize all that, which is you project the information you have into a shared vocabulary between text and images. And you use that into a large language model. So we used, in our case, Vicuña, which is a 7 billion parameter model that's open source. And what we did is we just fine-tuned it with the answers that we wanted it to give in the driving contexts. And so we used like a LoRa technique that was mentioned earlier that allows to reasonably cheaply adapt the weights of a model for like specific downstream tasks. And obviously, as is usually the case with modern AI, like the data is at the core of the whole like recipe. And so we had a bunch of like proprietary data, some open source data sets, some of them we labeled manually, some of them we auto-labeled, and that allowed us to apply some form of reinforcement learning from human feedback on the pre-trained model. And this is what we get. So you take a scene, this is in downtown London, like very close to King's Cross, and you get the model that is able to just narrate the scene, what it's observing. So I'm stopped behind a red bus, now I'm accelerating from a stop position, turning right to continue on my intended route. A bit slow, overtaking the bus that is coming to a stop, etc. So it's giving very like sensible answers and descriptions around the scene that it's observing, and we see King's Cross right there at the end. And so this was like our own model driving there. And we also like built a chat for it so that we could like kind of probe into like the system and see what it understands. So here, like the car is stopped behind pedestrians. We can ask it, why are you stopped? I'm stopped because the traffic light is red. What are the top 3 hazards that you're paying attention to? So it gives a sensible answer. I'm paying attention to the cyclist. I'm paying attention to the traffic lights and the pedestrians that are crossing the road. Why is that? Okay, yeah, I'm paying attention because they can impact my safety and that of the other users on the road. And when can you go? I can go when the traffic light turns green. So as you can see, these are all like fairly sensible answers. Second example, there we go. So what's the weather like? It's rainy. So again, this is like one of our models driving at that time. Do you drive differently when it's raining? Oh yeah, if it's rainy, like the road can be slippery, so I have to be more cautious. How come? Slippery, visibility might be reduced as well. And when will you go? I will go when the black sedan in front starts moving. Finally, when will it stop raining? So I cannot predict when it will stop raining. And the last question, is it true that it always rains in London? And it gives the politically correct answer that no, it is not true. However, it is known for its rainy weather. And personally, I moved there 6 months ago, and I've been very pleasantly surprised. So I don't think that is actually true. All right, so I'm done with the Lingo 1 model. And so now what are the future directions? So the first one is multimodal training. So what do I mean by that is, so we have a data set with videos of driving, we have the actions that are taken there, but we also have descriptions of the scene. And so the idea behind like multimodal training is combining the two. And at its core, there's this belief that a paragraph of text contains a lot more information than the millions of pixels that you have, or at least that the information is way more condensed. And that by combining the two, we can have huge gains in terms of data efficiency. And so this also, by predicting text from videos, it can boost like the performance in terms of representation learning, so that the model encodes knowledge about the world that is more aligned with the way us humans think. And the second one, also fairly interesting, is what I call like common sense reasoning for driving. And so here we can imagine having two systems in parallel. One, the driving model that has to think quite fast. So for those of you who are familiar with the think fast, think slow paradigm. So the driving model is going to think quite fast, and the language model is going to reason at a slower speed because it has to make more complex decisions. And having the two interact can, we believe, boost performance, where whenever there's a scene where you need to reason, then the language model is going to be able to do that and then pass its conclusions to the driving model that can then perform better. And so those last two themes are things that we're currently exploring. So that's it for language, and now I'm moving to world models. So what is a world model? So the premise behind this whole project is that in order to drive well, the model needs to have an understanding of the future and how it can evolve. And so if you take this image there, okay, you're moving on the road, there's the white car coming from the left. Okay, will it pull, will it go forward, will it stay stopped? Those are questions that the model needs to ask itself, either implicitly or explicitly. And by having the answers, can then decide how to drive better. So in this case, we're moving forward, the car was actually stopped, but being prepared for the possibility that the car will move forward is important. And so this is where world models come in. So what is a world model? It's a generative model that predicts what happens next, conditioned on some context. So what I call context here can be information about the past, so it could be past images, but it can also be some form of language, it can be some form of actions that we want to take, it could be the route that we want the car to take. And so conditioned on all that information, a world model predicts what's going to happen next. And so formally, it's like a distribution over possible futures. So here ST+1 is the possible states at one step in the future, and ST and CT are the state and the context at time step T. And the applications here are numerous. So we have like the idea of like learning dynamics of the world, and so being able to react fast to things that arise. There's the second one is counterfactual experimentation. So here you can swap the context, change it from, for instance, if it's text, you can change it from sunny to rainy, and then see what happens then, and see how it impacts the distribution over possible futures. And then there are things around model-based reinforcement learning, search-based planning. And so because here, the cool thing is that you can unroll this distribution by sampling multiple times one after the other. And that gives us a possible set of futures, and then you can pick the one you want if, for instance, you're doing search-based planning and are trying to maximize some desired outcome. We're not the only ones thinking it's a good idea, so here is a bunch of like videos that are generated by models from other companies. We recently added one from Sora. As you can see, it's very stylized. And yeah, this is like currently like a bunch of models that can do generation of driving videos. And this is our own, so GAIA 1. GAIA in our case stands for Generative AI for Autonomy. And here like the image was built using a combination of images generated by the model. And so this is the most technical slide I have. After that, it's just videos, don't worry. So what is the architecture that we use in GAIA 1? So it's just essentially a large transformer that operates in an autoregressive fashion. So it's slightly different from diffusion, which is another technique used for generating images and videos. And so here the idea is you take your video and you actually chunk it into small pieces, and each piece becomes a word, and you train your model to predict what the next word looks like. And that's at its core. It's very similar to something like ChatGPT, where it was just trained, okay, predict what the next word is, and you build autoregressively. We take that because, we've transformed the video into words. We can also use regular words, and we can use actions as well. And so we train that on the task of predicting what the next word is. In this case, it can be a patch in an image. And this is what we get out of it. So this is unprompted generation, so no context at all. Just from scratch, the model can generate a bunch of images like this. So we have a fairly good variety here. We have some night driving, some in the rain, some with like specific turns, roundabouts, some like agents around. Fairly diverse, I would say. We can do the same by conditioning on a given frame. So you take, for instance, this scene where you have a car pulling out on the left, and then the model needs to just generate a possible future. And so if you sample multiple futures, you can see what the model believes could happen. And here, like the model has like two possible ones. One where the car actually pulls out in front of us, the other one where it backs into the alley. And so this kind of showcases the fact that the model has understood the possible futures and the fact that multimodality is something inherent in our world. Okay, so like I mentioned before, we can also do action conditioning. And so in our case, action just means like how we want the car to move. And so this is a bunch of possible things. So we ask the car either to turn left. So interestingly, like we see that it generates possible futures with the car moving on the road, swerving. The one on the bottom left was particularly interesting to me because when the car passed the curb, we do see like the camera kind of wiggling, which was kind of neat. Other example, so I mentioned like language conditioning. So we can ask for sunny conditions, rainy, foggy, snowy. There's not a lot of snow in London, and still there was enough data for the model to be able to generate this. Interestingly, for rainy, as you can see, when it rains, we do get a lot of rain under the camera lens, and so the model has picked up on that, so it just generated a drop right there, which is kind of neat as well. And we can combine the two. So language and action conditions. So here, start behind this red bus, 15 meters behind, and the action is accelerating to the right, and then we let the model do its magic, and it generates maybe a bit too close to the bus, I would say, but still, like you overtake it, and then you keep driving on the road, and all this is completely generated. Like there is no other form of prompting beside the action and the language. All right, and so what are the next steps for Gaia? So the first one is how to like integrate into our driving model. So like I justified before, yeah, world modeling is something that we believe is essential to drive better. We can scale everything up to make the images even nicer. We could generate multi-views of the same scene, multiple sensors, so we could generate radar data. And then, a natural use of a model like this is to have a simulator where you can train, where you can evaluate the car and the models in order to boost performance. And on this, I will conclude. We are hiring. We have 2 offices, Mountain View and London. Feel free to come and reach out to me or go on our website. We also have a blog post with a lot of information, some research papers. So thank you for your attention.
Thank you very much, Remi, for your talk and sharing your work with us. Yeah. And now it's time for the questions from the audience. And raised hands here. And also there. So just a little bit of patience so that the mic reaches you. It's a big room. Elin.
Thank you so much for your talk. You mentioned earlier that old systems used a lot of rule-based determination, and a part of the strength of that is that you have absolute control. And I'm wondering how you're thinking for this type of system. Do you think that we can completely get away from rule-based systems as like a combined approach?
Yeah. That's obviously a very good question. We are attempting to demonstrate that data is enough. I do think that on the verification side, having some rules and having a way to design, like test suites with all the scenarios that you want should allow to verify a system in this way.
Thanks.
So we have hands raised here, and then one in the first row as well.
Hey, great presentation. I actually have a question regarding how you said that you use natural language to justify the decisions taken. I'm not sure I fully understood whether you then use that to generate your plan, but how did you validate that the reasoning provided by the LLM was actually based on what what the system was doing, rather than just giving a okay response?
Yeah, so probably, so Lingo 1 right now is a sort of backseat commentator. So there is no coupling with the driving itself. It's simply a model that's able to explain what it sees, but the driving is commanded by another model. And yeah, what I meant is, in the future, we would like to combine the two together. And in terms of guarantees, that's obviously like always the big question with end-to-end systems. Verifiability is something that like we're committed to, and obviously there's a lot of work left to do that well. Yeah, that's kind of it. Happy to debate about it some more.
Thank you. Next question.
Thank you. Super interesting. Coming back to the fast thinking and slow thinking, what's happening if the sensors fast thinking say one thing in this context, and the interpretation of the slow thing in certain cases could say something different? Who has priority in that case? Right. Thinking in the context of a on-the-road vehicle, of course.
Yeah, and so that echoes a bit the question from before. Yeah, you know, like we are building the systems right now. I don't have like a clear answer of what is better. I would think that, you know, like the slow thinker has priority, and then the like fast thinker is there to action on top of the slow thinker that would have like priority over it. Yeah, I do think it's a bit like, you know, us humans, right? Like we have, when I'm driving most of the time, I'm not really thinking, but there are moments where I'm like, oh, I might need to reason about like the next 3 seconds in order to make a decision. Once that decision is made, I just move the arms and the legs accordingly.
Thank you. And we have time for a last question.
Yeah, thanks for the nice talk. I have a question about the prediction, like the future prediction model that you had. Do you sort of try to train the model to predict events from different, in some way to speak, equivalence classes? So for example, it might not be so interesting to have 2 predictions, one where the car moves in front of the driving car at 1 meter per second versus 2 meters per second, but it might be interesting to have, you know, predictions where the car moves at 1 meters per second and then at 20 meters per second, so one could divide them into different classes.
Yeah, so for the moment here, it's purely the data we have, and the data defines the classes that you end up with. So no, we don't have a lower level control over like the generation in terms of, you know, like we want this object to move at a certain speed. However, we have some ongoing work. I didn't have time to show it today, but where you can add some form of control over dynamic agents in order to generate scenes more accurately. Happy to talk about that some more.
Thanks.
Yeah.
Thank you so much, Remi, for coming here and being with us. These flowers are for you. Please, let's give a round of applause for Remi.